more than that. We have people applying or using PyLops for applications in medical imaging and in astrophysics as well, showing that the actual library and the framework is very generic and very general. And you will see some short introduction about the library itself. I will also try to give you a flavor of one of the latest developments that I find quite exciting, the introduction of a GPU backend with the help of cupy and, in a way, partially cuSignal, which, as you will see from a user perspective, is very similar, very easy to use compared to the standard CPU backend, but it could give you extra speed in your computations. And you will see later from Lukas and David how this library has been used for some of their quite cutting-edge research. From what you see in my tutorials and in my slides, it's something fairly basic to get you introduced, but you will see how eventually you can really use this library to also do advanced research. So before I start with the library itself, we need to make sure everyone is in a way familiar with the concept of inverse problems. And I'm going to start with a very simple example. It's an example that occurs in many fields and for in physics. We imagine that we're recording some data that is a band-limited version of the subsurface, where the subsurface is, in our case, can be represented by a number of spikes that could be in the seismic domain, for example, reflectivity of the Earth. And the problem that we want to solve is to remove the effect of this wavelet or this convolutional filter to be able to get access to high resolution model in our case of the subsurface, or in this case of a simple 1D time series. To be able to solve the inverse problem, the first thing we need to be able to do is to formulate the forward problem. And here the forward problem can be seen as a convolution of the model with the filter. If you remember, or if you have done some basic inverse problems course in university, generally what you are taught is that you have to be able to create a matrix which can express the operation, in this case, the convolution. And this is very easy. You can make a matrix and place the filter along the diagonal and the extra diagonal of the matrix, making a third-place matrix. And if you do that, you will be able to just take your matrix and invert it or feed it to an iterative solver. And here you can see what actually you can do by using pure NumPy and SciPy in Python. You can create your model with a certain number of samples. Here I'm actually using a small utility routine in PyLops, but it's very similar to the conv matrix that you, for example, have in MATLAB, and you can find many online for Python. You can then, since you have your matrix, apply the dot product and create the data. And then you can feed these to any iterative solver that is available in SciPy. So what the problem is that when you start dealing with much bigger data and much bigger models, this problem doesn't scale very well because your matrix becomes bigger and bigger. And so you end up with problems both in terms of memory and computations. How can you solve this problem? In many disciplines, we have been solving large-scale inverse problems for quite a long time. And the way you do that is to use the so-called concept of linear operators. That is not new by any means, and is not only implemented in PyLops. You can find other libraries in other programming languages that implement the same type of framework, the same type of philosophy. The idea of a linear operator is very simple. You just need to be able to write this piece of code that if you feed a vector in the model space, will give you a vector in the data space. And also a second piece of code that if you feed the vector in the data space, will give you the vector in the model space. And this second piece of code will mimic what is called the adjoint of your matrix or operator. So if you have a matrix, the adjoint is nothing more than transposing a possibly complex conjugating. In this case, you will need to be able to find a way to express in computer code this operation, even if you do not have access to the matrix itself. And if you can see with PyLops, the code is very similar. The only change that we make, we use this convol 1D operator. that is a linear operator that mimics the effect of a convolutional matrix, where the forward can just simply be implemented using convolve, for example, NP convolve or SciPy convolve, and the adjoint in this case, you can easily work out that is the correlation. So you can use the correlate functions in NumPy or SciPy. Also, to try to make the library as expressive as possible, we overloaded the star and the at operators. The application is very easily expressed as if you were to write math in your paper. And finally, because of the way we created the library, we can feed the operator, in this case, the convolve operator, into any of the sparse solvers in SciPy, as well as some of the other solvers that we implemented ourselves. And you will see a couple of them later. What is also, as I said, exciting is that now if you have access to a GPU, you can very quickly change your code. Basically, you will change everything that is an NumPy array into a CuPy array, either directly creating it or transferring it to the GPU using the CP as array routine. And you will then rely on the PyLops solvers that now are able to handle both NumPy and CuPy arrays. And you'll be able to solve the inverse problem now on a GPU with, as I said, very, very little code change. So this is the history of the library, just to put it a bit into context. I call it library, but I will probably better refer to it as a framework, because now the main library, PyLops, is definitely the most mature and the most used, but there is a framework of other tools around that I'd like you to be aware of. So the library, as I said, was open source in 2018. At the start, it was sort of a toy project by myself, trying to improve my Python skills and trying to write an objective-oriented library with a purpose. And later on, luckily became something a bit bigger, a bit more important. It took a few months to get some people using the library and also getting some people in the CondaForge community allowing us to get PyLops in CondaForge and making it very easily accessible to everyone. In the next 2 years, we did quite a lot of development of the main library, and also some experimentation that resulted in 2 sisters libraries that, if you're not familiar, they are still in a much more experimental phase, but feel free to take a look. And also, if you're interested to contribute, we will be very happy. The first one is what at the start we call PyLops+cupy. It turns out that it was much better to implement the GPU backend straight in PyLops+cupy, as I said. But this library started as an attempt to implement some of the operators using PyTorch, and revealed actually quite useful, because we created a very tight link between PyTorch and PyLops, allowing, any of PyLops operators now to also be able to be included in PyTorch AutoGrad. So if you do machine learning, and especially if you do some machine learning that requires also some physics-driven operators that is not very easy to implement in PyTorch, you can use the link with PyLops. As I said, we also did quite some work in terms of writing a distributed version of some operators in that. In case where we really need to deal with very big problems, for example, very big model vectors and very big data vectors. And one of these problems will be also discussed later on by David. Finally, very recently, there has been 3 new additions. The top one was contributed by a former colleague of mine in Edinburgh University. We did our PhD together, and I think is actually online today. He was able to take the curvelet library, very popular curvelet library in C++, and bind it in Python, adding it a PyLops operator. So now you could also use curvelets as one of your sparsity transforms if you were to do any work, for example, in the domain of seismic reconstruction, or, for example, medical or seismic imaging. We added CuPy, as I said, and also very recently we just created a small sister library with so-called proximal solvers that are a bit more advanced solvers than most of the one available in the main library. They can solve complex non-smooth functionals. So if you're not aware of what proximal solvers are, or you see that some of your problems cannot be solved with the solvers in PyLops, take a look, because maybe they could actually be useful for you. The last slide is about how the project evolved in terms of stars. And this is not just to show off, but is to show how the project is gaining more and more popularity continuously from the beginning until now. But what I'm actually more proud of is the fact that we have more and more contributors, and also more and more external projects that use PyLops as a requirement for their code or their open source development themselves. And with this, I will just leave a summary of all the possibilities that can be done so far in PyLops. And here, the most important part of this slide, the link, the organization, where you can find the PyLops library, all of the other libraries I've been talking about, as well as some repositories with tutorials, for example, the one of today. Let me see, if I switch, do you now see my Safari? Yes.
Yes.
Great.
Yeah, we do.
Okay, so what I want to show now is, first of all, that where you can access the tutorial. Yes?
Just, yeah. We lose you every couple of minutes. Your sound drops a bit. Maybe if you stop video sharing while you're screen sharing, that might help the bandwidth.
Oh, yeah, that's a good point. Let me stop video sharing. Nobody needs to see me.
Cool.
Tell me if it stops. And also, if anyone has any question at this point, just unmute yourself and speak, and I'll shut up. Otherwise, I continue. You can ask questions or on the chat. Okay, seems like everyone is still on board. So as I said, this is the main repository for today. You will have the tutorials that I'm gonna hopefully go through, and also the slides you have just seen. First of all, let's try to go through the first tutorial, where we are actually gonna see some PyLops code and Python code to solve the example I've been talking about in the presentation, the problem of 1D deconvolution of a time series convolved with a wavelet. If you have access to a GPU on your own machine or by any other mean, I will suggest going for that route. But if not, and if you really want to try using PyLops with GPUs, which I recommend, or if you want to do some machine learning, you may be aware of Colab, which is a great environment for being able to use GPUs and use free compute. But I will say, there is a disclaimer here. We are providing you with an installation script within the repository. And by running this installation script, you will change a bit the basic Python installation of Colab, adding some of the libraries that we need. For example, cupy with the right version and PyLops. This generally works, but as a disclaimer, Colab sometimes changes version of Colab libraries change. So these may break at some point, but if you realize before me and you are willing to use it, just feel free to reach and we'll try to get this running again. At the moment, this seems to run, which is good. And we're gonna start, as I said, with the 1D example. And what we're gonna do is go through the code, not line by line, but just to give you an idea of what are the main operations that are required to solve this type of problem. So we're gonna start at the top. This is some sort of boiler code that creates a model vector with a few spikes and creates a Ricker wavelet. The interesting part here starts from here downwards. So this one is discouraged, as I already mentioned. We don't encourage to solve this type of problems by creating dense matrices and throwing dense matrices as iterative solvers. But if you want to experiment with it, you can uncomment these two lines. You will create a dense matrix with this auxiliary routine, which is equivalent to performing a convolution of the filter with the input signal. And you will wrap this into the matrix mult operator of PyLops. You're actually making it part PyLops metrics to make things a bit faster, but still you realize that solving the problem this way is not really as fast as you wish. So why PyLops comes to help? Because here you can create a convolve 1D operator using one of our PyLops operators. You will provide the size of your model, the impulse response, offset, which means which sample of the impulse response you are at time 0. And also you can provide different methods to apply the convolution. Here we choose to use FFT convolve method. Let me skip this for a second. At the bottom, you see, as you already seen in the slides, if you apply the operator times the model, and I'm going to run this piece of code, this will create your data. But you see that something pop up in the print saying .test passed, and then some numbers. What does this mean? Well, the .test is a very powerful piece of equipment, let's call it like this, when you develop a library like PyLops and when you develop linear operators. And why this is so important? Because, as I said, a linear operator is a pair of pieces of code, a pair of codes, one that applies the forward and one the adjoint. But how do we ensure that what we are doing is correct? How do we ensure the forward and the adjoint are actually the forward and the adjoint with respect to each other? If you could make a dense matrix, the adjoint, as I said, will be easy. You transpose and that's it. But if you write computer code, sometimes it's not even easy on pen and paper to really figure out what is the adjoint. So you need a lot of trial and error, both on paper and on computer. So the .test is a mathematical test. If you're interested, you can look more into the documentation to understand exactly what the test does. But it's a test that performs the forward and the adjoint on some random vectors. And if inequality is satisfied, means that your two implementations are likely to be correct. When I say likely, this means that the condition from a mathematical point of view is only sufficient, is not necessary. But from a practitioner point of view, people, including myself, see that if the .test is passed, you have a very high chance that your implementation is correct. Let's now move on to solve the problem. We have created the data, we have the operator, and we're going to use one of our sparse solvers. The reason why we use sparse solvers and the reason why we invent solvers is that they are very powerful in the sense that they allow you adding extra information to your problem. For example, to solve a least problem, you can add extra information in the sense of a Tikhonov regularization. You can say your norm should be small. But problems like the one we are trying to solve now, they have an extra prior information that you could fit to your solver. You would like your model to be sparse, meaning that you would like most of your model to be 0 and only a few samples to be different from 0. And if you were to try to solve the convolution problem here using a least square solver, I actually encourage you to do it as an exercise, you will see that if you have a very small regularization, your solution would be very ringy because you're trying to deconvolve or reconstruct high frequencies and low frequencies that are not present in your data. Or if you make a very high regularization, then your solution will be too smooth. On the other end, if you use a solver like Vista, this allows you to enforce sparsity and you will get a very nice solution, as you will see in a second. What you can see here is that all the operators work this way. All the solvers work this way in PyLops. You have to pass the operator, the data, and a number of optional parameters that change from solver to solver. But most of the time, one of them is called EPS, which represents the weight that you give to your regularization term. And very likely, for all of the solvers, you also would like to choose how many iterations to run it for. Finally, this show equal true will give you some verbosity while you run the code. So let's run the code now, and you'll see that very quickly you will get down to 200 iterations. And here is what you have seen in the presentation, the operator, the model, the data, and the reconstruction, which is almost perfect. So what can we do if we want to use GPUs? And I already shown in the pseudocode in the slides, you only need to ensure that everything that goes into the operator and the data itself, they need to be passed to your GPU. So let's run now the code with the GPU. And the result is identical, but you see that now it takes 0.49 seconds versus 2 point something seconds. And this is really using small models. So you're not really using your GPU to the full extent. Probably most of the threads are underutilized, but this shows already the value of using GPUs. And finally, I'm running this function that is called deconv and is available in the repository, which just loops over multiple models with increasing size and computes the time it takes to run the inversion. And this is to show how the performance of the GPU and the CPU compare with increasing number. So it'll take a few seconds, and when it pops up, you'll see that the increasing time of the CPU is almost linear, but the one of the GPU is almost flattened because for most of the cases you were underutilizing your GPU, and when the model starts to become bigger, then you take more and more advantage of the threads of the GPUs, and you get a very nice change in terms of computational speed from one to the other. I have 5 left. I don't want to take any time from the other 2 speakers. So what I'm going to do, I'm going to very quickly give you a flavor of what the second book is about without running it, and you will be able to run it yourself. This is one step further. We are not dealing anymore with very simple 1D examples that you could potentially solve using dense or sparse matrices. Here we are dealing with the problem of seismic interpolation. Let me just go to the equations. The problem of seismic interpolation is fairly simple in terms of formulating the problem itself. It's very hard to solve. So in seismic interpolation or seismic reconstruction, you generally start with the data that you're able to acquire in the field. And you can imagine that you will like the data on a very finely sampled regular grid of receivers, but you can only acquire it in generally a sparse, I will say coarse, not to make a mess with how I generally refer to sparse. So a coarse representation where you have either coarse and regular sampling or coarse and irregular sampling. Your forward model is simply what we call a restriction operator, just an operator that takes the traces where the data is available from your model, which is the finely sampled representation. What is difficult, as I said, is inverting this problem. This is a problem that also is very popular in computer science, generally referred to as in painting, and it's difficult to invert because if you just try to invert it without any regularization, you will get stuck after one iteration of no matter which solvers you use, and the result will be something that is of the size of X, but it will be 0 everywhere other than in the traces where your data is available. So definitely you need to add regularization. And there is a long history in geophysics of different ways to add regularizations. And here we are trying with 2 different options. One is a linear radon transform applied in sliding windows. The other one is a full FK Fourier wave number transform applied in patches. And what I want to show you here is, I'm not going to go through the definition of the problem. I just want to show you how you will handle sliding or patching with PyLops. So this is one of the most, I would say, complicated ways to use operators in PyLops. We have sliding 2D, sliding 3D, and patching operators that basically take a model, which is either a 2D or 3D representation, for example, in this case of seismic data, and divide it into either slices in the sliding approach or patches. And when I say slides, means that the time is fully taken and you take only a few samples in the spatial direction, while the patching, you have small patches in a small number of samples in any direction. And then on each of those patches or slides, you can apply another operator. So in this case, we are applying the radon transform for each patch. And once you create it with this basically this pattern where you create an operator and you feed it with to your sliding 2D in this case, then you can use it as very powerful either preconditioners or regularizers to solve your inverse problem. And I'm going to leave you just with a plot that hopefully clarifies more what I've been discussing. So imagine that this is your data, your full data. Your sliding transform will take a few samples in the x direction and apply the radon transform. And this will be what you see here. We'll take a few more and apply another radon transform. And you see that this repeats over and over again. When you have a subsample data, what happens if you apply the radon transform? You see you will get a lot on smearing due to the fact that you have some zeros in your patch. And so the radon transform will basically smear out what is available in the few available traces. So solving this problem with a sparsity solver allows you to basically get out the most representative samples that can still represent what is available of the data and extrapolate outside where it's not available. And you see that your reconstruction here, in this case, after 400 iterations of Vista, is very good compared to the starting point. So if this was the initial error, this is the error that we get now. As I said, there are many, many methods in this domain. And you will see if you want to run this notebook below, you will also you could also use the FK transform, and you could also use, for example, one of the most powerful transforms, curvelet transforms, as I mentioned before, thanks to Carlos. At this point, I hope that you have a better understanding by now what PyLops is, how it can be used both on CPU and GPU, and how you can go from simple to more complicated problems. And hopefully with Lukas and David, you will see that the bar can be raised even higher than what I've shown in these two tutorials. So Lukas, I'll unshare and it's up to you now.
Cool, thanks, Matteo. Hey, it's a good time for if anybody's got any questions, just off that first part as well. Now would be a good time to unmute and.
I play the trombone.
Matteo, just a question on your use of PyTorch. So
yeah.
You have PyTorch involved in your PyLops already. So can I just say, for example, take a well log with some fashes, and when I run my inversion, use that in some way directly inside PyLops to come up with a machine learning classification for my inverted data?
Yes, well, I'm not using it for that problem, but yes, you could basically couple, for example, if you start from a data and then you put it into a neural network and you try to estimate facies labels. There are a few papers, not by myself, but that they take the estimate and then feed it into a modeling operator to get the new data, and then they use that as part of the cost function. So to get the new data, you need to apply basically a convolutional modeling or a AVO modeling. That's where you could use PyLops and everything will be linked together in the AutoGrad chain of PyTorch. So you get AutoGrad for free without having to re-implement, for example, PyTorch. That's
so
the reason.
In essence, I can get say something, a result like P cube, but not in a say Bayesian domain, just in a machine learning domain.
You could potentially, yes, but you'll have to do it yourself.
yeah, of course. Thanks.
You have all the tools to do it.
Yeah, good. Thank you.
Anyone else? Or we move to Lukas?
Just a very quick question here. Have you looked into the new sparse library that is kind of hoping to replace the SciPy sparse?
I have looked into that. I have not tried it yet, but yes, I did look. And I think sparse, SciPy sparse is quite good, but it doesn't have too much. I think this library could be very powerful. And I think there are still places where you want to use sparse metrics is not operator. We were actually discussing with some colleagues a few days ago, for example, if you want to solve PDEs, for example, in frequency domain, in that case, probably it's much faster to directly inverse a sparse metric. So that's a good suggestion. I will definitely look even more into that.
Cool. If there are no more questions, we'll head on. Lukas, take it away.
Great. Can you hear me?
Yep.
Is the audio fine? Great. Thank you very much for having me. My name is Lukas Mosser. I'm a principal geodata scientist in Earth Science Analytics and also active member on Swang. You can usually find me as at lmoss on Swang. Before I start to tell you something about how we used PyLops in some of our research, I just quickly want to say that the tutorials that Matteo showed before and also all the tutorials that are available with PyLops have been a huge learning resource for myself and my colleagues to get started with PyLops itself. They're some of the best resources that I could find on the internet in terms of tutorials walking you through a library. So I highly recommend going to check those out if you're keen on getting started with PyLops. So just to head it off here on our application, what I'll be presenting today is how we try to estimate what's called relative geological time from seismic images. It's a bit different in terms of an inverse problem as what Matteo showed before, but PyLops was a very good use case for our application, and I hope this will give you a good impression for a simple problem and application of these operators that you find in PyLops. So what is relative geological time estimation and why do we care specifically? Well, one of the things that we're interested in Earth Science Analytics is to estimate the properties of rocks in the subsurface and reservoir properties. And one thing that we know about these sediments and geological layers is that at the time of their deposition, we can usually correlate these laterally. So if you have something like a riverbed, you know that the riverbed follows on the surface, and at the time when it sort of deposits, we can laterally follow the channel sands and the high porosity, high permeability regions that are of interest to us when we go looking for hydrocarbons in the subsurface. And so what we want to do is we want to be able to estimate the properties of these rocks from seismic images and be able to follow these geobodies laterally. But of course, we know that due to geological processes such as burial, uplift, erosion, various deformations over the millions of years that these sediments have spent in the subsurface, this lateral continuity of these interesting sediments has been broken. And so what we want to do is we want to be able to restore this lateral continuity to then actually be able to predict properties within them. So this could help us possibly to make better predictions of the properties in the subsurface. And specifically what we want to be able to do is we want to be able to estimate the time within a seismic image of when these geobodies have been deposited or when horizons and strata have been deposited, and we call this time the relative geological time. So lines of constant geological time are basically the horizons that we see in seismic images. Now, this work that I present here today is, of course, my name was on this, but this is in collaboration with my colleagues at ESA, and it's based on previously published work by Ximing Wu and Dave Hale, where they have actually figured out how to do this based on seismic images. And so just to give you an impression of what we want the result to look like, this on the left, you can see here a seismic volume. So this is just a 3D cube and taking a cross section from the seismic cube. And we want to find an operator that allows us to take the seismic image and create a flattened, let me just minimize this here. I don't know if you can see that. That allows us to create a flattened seismic image. So here we want all the horizons that we see here dipping on the left, and also the faults are deforming and shifting these individual fault blocks relative to each other. We want these to be restored in a way that we can laterally follow the horizons, as if they were deposited at the geological time when they were deposited. And the way that we do that is we need to find a displacement field that tells us how do we have to shift each voxel or each sample in the seismic image. By how much do we move it upwards, downwards, laterally, to restore this, this flattened representation of the seismic image. And finally, we want to also obtain the so-called relative geological time. So here you can see that if you were to take a ISO contour through this relative geological time attribute, then you would be following the horizons that you can see in here that belong together in a geological consistent way. But of course, you can imagine that this is a pretty ill-posed problem, which means that it's not clear without any constraints how you need to shift, for example, this fault block relative to that fault block without having any additional knowledge. Regardless, for the sake of simplicity, we're going to treat here the completely unconstrained problem of trying to restore the lateral continuity of these horizons. There's also a constrained version, which is a bit more involved and would go beyond the scope of what I can show today. But I think we're mainly here to talk about PyLops, and for this, it will be completely sufficient to talk about only the unconstrained problem. All right, so a little bit of math. I'll try to keep it simple, but bear with me. This is might look a bit overwhelming, but the basics here is that we can define the relative geological time as the constant time that we have in our seismic image. So this is just linear time in the seismic domain today, and adding a shift field. And what we want to find is really this shift field or displacement field of how we have to move the voxels in the seismic image to restore the order in the geological flattened time. And there's an assumption that we make here, which is that the gradient of this relative geological time volume is approximately the same as the normals of our seismic image. So if we were to approximate our image or compute gradients with respect to the image itself as we have today, then we're basically looking for the normal vectors of the horizons, and we make this assumption that the relative geological time, the gradient of this, is roughly the same as the gradient of the seismic image. And we have ways of computing this, for example, through the use of so-called structured tensors. Now, there's a bit of a mathematical derivation here, where we can reform this into so-called seismic dips, which tell us how our horizons are dipping in inline and crossline direction. And you can see that there are some gradient operators here in the inline direction, crossline direction, and also in the time direction. And what we really want to end up with is this form where, in addition to reshaping these operators, we also sprinkle in some empirical weighting to measure how important actually it is to constrain to these local vectors. And also we make the assumption that the shifts in the vertical direction should change in a small way, so that we don't have huge shifts or changes in the shifts in the time direction. And this allows us to come up with a operator form that was similar to what Matteo showed before, which is it's just a matrix operator form. And you can maybe already see where PyLops might help us. Here I just added another image to show you what these dip vectors look like. We pre-compute these actually for the seismic image. And these give us the normal direction to these horizons. So if you have this horizon here, then maybe the vectors actually should point upwards here. And you can see that when we visualize these dip vectors locally, these give us the orientation of the seismic image along these horizons. And we can use that as an input to reconstructing this relative geological time volume. So we started off with this operator form with these derivatives in the inline, crossline, and time direction. We also have some constants that tell us how to weight these contributions. And what we want to end up with is this shift or displacement field. And on the right side, on the right-hand side, we also have these dip vectors, again, weighted by these these empirical weighting matrices. And what we're going to do is we're going to solve this in a least squares sense. So we have a new least squares representation, and this we can express as a simple linear problem where we have an operator A times S equals B, and we're going to try to solve for this shift displacement field. And we actually do this by a conjugate gradient method. This is all explained in the paper by Ximing Wu and Dave Hale. But here comes the challenge. These seismic volumes that we're actually applying here, they can be very large. So we often want to look at seismic images that are maybe 1,000 inlines by 1,000 cross lines, and also 1,000 samples in time. So when we look at these operators here, the ones that we're dealing with, then if you take this weighting matrix, this is a 3n by 3n diagonal weight matrix. So you can probably still represent that as a sparse matrix. But then we also have these finite difference operators. And finally, we also have this shift vector. And if you consider this one of these operators and you're dealing with 10 to the 9 samples in your volume, then even representing this as a sparse matrix, the entire operator is just going to eat up your RAM, your memory of your computer. And even for large workstations, this will be very challenging. So what we're looking for is a much more elegant way of applying these individual operators in this setting. And of course, PyLops has many of these functionalities. It doesn't require us to actually explicitly represent any of these matrices that we see here. So really, PyLops came to the rescue here, and I also show here a quote from the actual publication where they mentioned that when they had implemented this, they didn't actually form any of these matrices. They implemented a similar version of these strided finite difference operators themselves, but we're using a Python ecosystem, and we're looking for a good solution that would work with the rest of our code base. And so PyLops was a great library and resource to have here. And what I want to show here on this slide is really how verbose and explicit you can go from a math representation, such as the one on the left, to a code representation in PyLops. Of course, this is not the full code. It's a pseudocode to show you what the workings are, but many of these operators can be applied one-to-one to be able to reproduce these implementations. And so one of the things here, for example, one of the operators that we use quite often, and you can see here on the left side on the operators, you have these first derivatives in the x, y, and time direction. And we simply define these as a pre-configured operator in PyLops. And we can take these operators together with the weight matrices and stack them in a way where we don't actually represent any of these matrices explicitly. So this is still an operator that just tells us how, if we apply this operator, how are we going to reshape and add and combine these various derivatives that we have here on the left. So you can go from this math representation like this linear form straight to actually solving your problem, in this case using conjugate gradients. And one of the fascinating things is Matteo and the people that are working on PyLops, they also ensured that this can function with existing other libraries, such as the sparse libraries in SciPy, and you can directly use these operators in a conjugate gradient framework, for example. So you don't even at the end have to turn this again into a matrix. You can simply input this as an operator, and it will work to actually solve this linear problem. So what are some of the powers of PyLops from having worked with PyLops over the last year? The general items to us, or to me specifically, is that we can go straight from a math representation to a code representation. Many of the operators that we encounter in the mathematical derivations, we can directly encode into a code representation. It's quite verbose, but it is very precise. And what I mean by that is you will find operators such as that are called first derivative, second derivative, directional derivative. So it tells you really what it is doing and how you can use it. And what you see is really what you get with these operators. And of course, the integration with other libraries is extremely powerful, that you don't have to adapt your iterative solver or something else to be able to interface with PyLops. And in our case, for this specific problem, of course, not having to explicitly represent the matrices was a key step to tackling this, simply because you would run out of memory for larger volumes. And many of the operators that we needed were already implemented. So only a little additional custom coding was necessary to get this to work in the end. And as I mentioned before the presentation, one of the best things about PyLops, I would say, is the documentation and the support. If you take the time from when we started with this to where we sort of were at the stage that we could have a working prototype, of course, with some precursor work around understanding the mathematics and everything involved, this literally was a matter of days to set something up that could give us the results that I showed you here in this presentation. So with that, thank you, Matteo, and to you and the developers of PyLops for sharing this great library and giving the chance to talk in front of you all. And for, of course, I have to mention here as well, Geoscience Australia, who provided the seismic data that you could see here in this presentation. So I'm happy to take any questions now if we have some time, or you can always find me on Swang as at Elmos. So thank you very much.
Cool. Thank you, Lucas. There was one question. Yes. Oh, maybe Matteo's answering it. Okay. It was on data transfer between multiple GPUs. But
all right.
Yeah, I'm writing.
Yeah. Cool. Was there any more questions for Lucas specifically? Oh. I had one. Did you have to go block processing out then for that relative geological time volume? Did you have to go and do something to address sort of large data set that you want to do that? Therefore, you have to start blocking, you have to start reconciling. And does PyLops actually help you with that?
Yeah. So initially, that was basically our fear that we would have to do that. It comes with its own problems to be able to do that consistently, the blocking for relative geological time. But if you actually use PyLops, because you don't represent any of the matrices in the operators, in the gradient operators, for example, you don't run into memory issues even for very large volumes. So we tested this up to a size of a few thousand inlines and crosslines and samples in time. And this still worked on a fairly beefy machine to perform the computation. You then, I think, run again into more the computational time challenge rather than a memory issue, that it just takes a long time on a CPU to do these computations. And things like CuPy would probably definitely help at that point to apply these methods.
Cool.
Hey, Lucas, just a quick question. When you do your geological reconstructions, do you say interpret on the seismic first in any way to build sort of a prior that you want to say flatten?
I didn't understand. What do we do with the seismic?
So the seismic example you showed was an anomaly faulted block. So do you say interpret horizons based on seismic reflectors that you want to flatten each one too? Or how I don't think I understand how that worked. Sorry.
Right. So this was part of what I showed earlier here, that basically, you're absolutely correct. Normally, you would interpret some horizons, and these would give you some bounding volumes where you know that the reflectors across faults correlate with each other. And there is an implementation of this, which is in the same publication by Ximing Wu and Dave Hale, where you can actually incorporate such constraints that come in the form of horizons or constraint points, so that you tell the relative geological time estimation algorithm which points across the fault, for example, here, should actually correlate with each other, which ones should be next to each other. In this case, we did this completely unconstrained, and this is the unconstrained version of that algorithm, which is also in that publication, but which also means that you will not necessarily find the right correspondences between these horizons. It will give you something that is locally flat, but not necessarily explicitly geologically consistent, following additional knowledge such as horizons.
Oh yeah, awesome, thanks.
Cool. We have another question from somebody on YouTube, actually. Christian Torres. So excellent. Does PyLops run 100% in Python, or does it call C++ code on the hood?
Yeah, I can answer this question and a similar question, or different question, but probably similar answer. PyLops itself is purely Python, which does not mean that the code that runs is purely Python. And I explain what I mean. We only use Python libraries, and the most sort of hybrid is NumPy, and of course Cupy. But by leveraging NumPy and SciPy and PyWavelets, for example, most of the code under the hood runs in highly efficient C or even CUDA, but none of the installation of C++ libraries, for example, is required when you install PyLops, because the requirements that we have, they already all provide pip and conda installed. The only library that will make you sweat a bit if you want to install it is the curvelops, and just feel free to reach out to me and Carlos, but we also sweat all the time because you have to install a few C++ libraries before you get to the point of using it in PyLops, but the rest should be fine. And the similar question is, does everything work on Windows? We have experienced that everything in PyLops works on Windows. I have no clue if Windows can even handle GPUs, so I don't expect that part to work on Windows, but the pure vanilla PyLops with just the CPU backend has worked on Windows for many people, as well as on Azure pipeline, so that should be fine.
Cool. One more question again from the Christian. Christian, sorry, is it possible to wrap functions from other libraries such as DeVito in PyLops operators?
Yeah, so that would be great. I know some people have done it. We have not got that implementation available, but if anyone wants to give it a go, I'm actually interested myself. So yes, for example, the library, the operator called Wavelet, DWT, is actually a wrapper of the PyWavelets. We have not re-implemented wavelets ourselves. That would be a bit stupid. But yes, you could do the Vito. I think it shouldn't be that difficult. And if you want, just reach out. We could even try to do it together. There is one more question. I think it's to Lukas. How about the condition number of the G matrix?
As far as I know, it's pretty poorly conditioned, and also depends on the constants, the weighting constants that you put into your weighting of the individual operators. So we did find that the convergence of this unconstrained problem depends heavily on the choice of these weighting constants. And at the same time, we did experiment with the constrained version, and that definitely gives better results. as you can see in the publication. But this also helps to constrain the problem better in general.
Sorry, if I could butt in on that as well, just really quick. In general, it's really hard to estimate condition numbers for matrices that you don't have a representation of, because you need to estimate. You can do it through spectral radius, or you can do it through obtaining an estimate of the norm of the inverse and so on. So it requires you to actually somehow invert the system. So these things are usually really, really hard to do unless you have a small matrix. But one of the nice things that you can do with PyLops is you can use eigenvalue algorithms that are implemented for matrices, but will work for PyLops operators as well. So after you have, for example, your largest eigenvalue or something, then you can use that in an inversion to set a regularization parameter or something, which will be something like a percentage of your largest eigenvalue, and that you will condition your matrix so that you know exactly what the minimum, the condition number of the matrix will be, because you're adding, for example, an identity with a percentage of your largest eigenvalue, and then you can properly condition your matrix. This is something that's actually really, really nice, and I wasn't able to figure out how to do that until kind of PyLops came along, and you can use these simple eigs functions, for example, in NumPy or SciPy to calculate them. So yeah.
Thanks, Carlos, for that recommendation. I have to say, my statement on the conditioning number is coming from what has been published on looking at that problem, but we haven't for the problems that we considered, and for these data sets that I showed, we haven't actually measured the conditioning number. But I think it would be good to go back now, and thanks again for that recommendation, to see if we can improve the convergence there by using PyLops functionality. I think that might help us definitely to improve the results as well.
Cool. Was there anything else, Lucas? Oh.
Not from my side. Thanks a lot for having me.
No, thank you.
Thanks, Lucas. Very, very nice presentation, a very nice use case. I think if people want to reach out to Lucas, I think he's very happy to discuss his experience, but it's very nice to see how different use cases come up, because people work on different problems and find the library useful for that. Shall we move on to David and give him some time? Are you there, David?
Yes, I'm here. So let me just start by sharing my screen. Okay, are you guys seeing my screen right now?
Yes, we can.
Yeah, we do.
Okay. So if I flip back, is good to you? Also?
Yes.
Mm-hmm.
Okay.
Yep.
Well, thank you. Well, yeah, thank you for having me. My name is David Vargas, and I am a PhD student at Utrecht University, working with Ivan Vasconcelos. And today I'm going just to give you a brief overview as to how we can use PyLops, how we particularly use it for our research. I pick a specific example that is scattering-based wavefield redatuming, but that is not to say that we use PyLops for things like wavefield interpolation, wavefield decomposition, and some other things. But today I'm just going to concentrate into this example. We also work in this kind of research closely together with Matteo. But let me just get started by motivating my talk by showing you this kind of traditional seismic velocity model. And in general, for people who are familiar with seismic imaging and all these seismic techniques, we usually have a set of receivers here located at the surface, and we send some seismic wave by injecting shots at multiple locations. Then these wave fields propagate, and they have to see things like overburdens and some of these horizons. And eventually you will have the reservoir here beneath. So the whole goal of seismic imaging is to come up with a representation of the subsurface and to identify some of these reflectors. Now, if you do standard reverse time migration at the reservoir level, this is what you observed. And clearly you see here that the reflectors are there, but on top of that, there are some other artifacts that might be misleading for an interpreter, right? Now, in 2014, there was kind of a paper with a new strategy that is called Marchenko imaging. And the idea with the Marchenko imaging is to basically use the reflection data and limited knowledge of the medium to come up with an image that looks like this one here. So you clearly see that most of the artifacts have been removed, and that now we have a better image, with high resolution. Now, at our research group, we are interested in exploiting these Marchenko imaging techniques to things like target-oriented studies, and to see if we can just push further this strategy to track some changes at the reservoir level. And here, this is an example of the case study in the Sleipner field that have been done with a different approach. But we foresee that some of these applications of Marchenko imaging can be translated into these kind of studies. Now, just to briefly give an idea as to how we can get an image of the subsurface. Traditionally, you will have a source that is injected at the surface level, and then this propagates, so a wave field is propagating to the medium, and eventually hit the scatter at the position X. On the other hand, the reflected wave are recorded here at the receiver's sites, and the strategy for image consists of take the back propagation of the receiver fields, and then at the position of the scatter, you basically evaluate this convolutional process, where the R represents the reflection response of the scatter. Yeah. So if we want to get a very good estimation of this image, basically we need to get a way to estimate the up and down going green functions, or the wave fields, here denoted by G plus and G minus, and then perform an accurate deconvolution process to estimate R, followed by the evaluation of the so-called imaging condition. Now, there are some other forms of imaging conditions in the world that do not necessarily are represented in terms of multidimensional deconvolution, but just a simple convolution. And now here, I'm just going to rewrite this in a discrete framework, because in what it comes next, so all of these expressions are written in this way, rather simple. But I want you to bear in mind that behind this simple matrix vector multiplication is just this convolutional operation followed by integration along the receiver's line. Okay. Now, for the purpose of imaging, let's assume we want to estimate the seismic response from a source that is located deep inside the medium at position X, and that this source, we want to basically estimate its response at the receiver level, right? So one of the common strategy consists of, okay, first you build a very accurate velocity model by means of full waveform inversion or travel time tomography. I mean, there are multiple strategies to do that, but that itself is, in one hand, expensive, and in other hand, might not always lead to an accurate enough estimation of these wave fields. Now, if we take the Marchenko extrapolation approach, it is enough for us to have, in this case, just an estimation of the direct wave, and together with the seismic reflection response at the receiver sites, we can basically use a convolutional model to estimate the response at the receiver sites from this point source here at position X. Now, this is what we get. In this panel, you observe basically offset and time, and this is the shot gather. If we select some traces and we compare it with a benchmark that is being modeled with finite difference, assuming that we know a very detailed model, now this is the result. And it looks pretty nice in the sense that not only kinematically, but also the amplitudes of these traces are really well reproduced. Now, what I want to do next is, what about a more complex problem? And for complex problem, I mean, just basically do the same Marchenko redatuming for this, for the case when I have basically put in between a solid body, introducing a very large contrast or impedance contrast. So also, I would like to draw your attention that inside this solid body, there's a lot of scatters, and this resembles what is known as the dirty salt. Yeah. So this will introduce a really high complexity to the problem. And clearly, if we now do Marchenko for these kind of problems, the reconstruction is not that accurate as we see here in these traces. Yeah. So we've been working on how to come up with some extension of the method for it to work in these kind of environments. And for that, we are using PyLops because, in essence, what we now solving is a rather larger system of equations. So now I would like just to draw your attention into the system of equation of a Marchenko problem. Here we have the reflection response that I was talking on, and we basically compose this matrix operator that we call the Marchenko operator. We apply this into the so-called focusing functions. I'm not going to go into the detail as to what it is. But we assume that we know at least a fairly good estimation of the initial focusing function, which is basically the direct wave of the green function that I showed in one of the examples before. And clearly here, if you want to estimate these focusing functions, you need to invert for them. Yeah. Now, here on the right-hand side, you observe basically the code and a snipe of the code. And I want to draw your attention as, here, how we can implement this into PyLops. Well, for this part, we first define a PyLops operator that basically calls a block PyLops operator. And clearly you see that basically the syntax resembles the algebra here, which is pretty convenient. Yeah. And also in the data vector is basically expressed the same way. Now, once we have these PyLops operators, we're just ready to call an external solver like LSQR. Yeah. And we feed it here with our PyLops operator. Now it's just a way, it's a very convenient way to implement a rather large problem. Yeah. Now this step is called focusing, and this is going to solve for the focusing functions. And then if we want to look for the green functions that I was referring before, we need to solve the redatuming problem. And that is basically applying this operator into the focusing functions, and that will give us access to the green function. Now, in the code, our matrix here, what I call M, is just basically this block matrix, where we observe here the identity matrix and also the reflection responses here. And then again, we just apply a matrix vector multidimensional convolution. And here we just see it as a way of matrix vector multiplication. Yeah. And that will give us access to the green functions that I was looking for. Yeah. So it's a very, very convenient and very, so I would like to highlight the expressiveness of PyLops when the time comes to implement this kind of operators. Okay. So how are we going to solve the problem I was referring at the beginning? Is basically came up with an extension of this Marchenko system of equations. And for that, we basically leverage in the availability of some of reference models that are there, for instance, typically used for migration. We can use them. And in this scheme, we basically propose what we call the perturbations in the reflection data. And for this particular case, I'm going to just introduce another kind of, so basically, yes, a different kind of reflection data and in the form of vertical particle velocities. And that will give us access to a band limited pressure wave fields instead of the broadband Green's functions. And here, this is how now my problem looks like. So immediately you see that this is an even more complex and large problem. So here we no longer have the identity matrix, but we have a more denser operator. But then again, if we want to write down this in PyLops, it's fairly straightforward and simple. So all we need to do is just again call our block operator, and we just fill it up with some individual PyLops operators performing multidimensional convolutions. Yeah. Okay. Once we solve the first step that is called focusing, now we are ready to solve the second step that is redatuming. And for that, I would like just to for you to look at how we define these matrices in PyLops. Then again, we just use our block operator and we fill it up with individual vertical particle velocities in the forms performing multidimensional convolutions in this way. Okay, and then again here, all this very large and perhaps rather complicated equation is reduced to a single line of code here. Yeah, so here this V operator is this large one here, and then the vector here is just the perturbations in the focusing functions that you see here. Now you add this with the perturbations of this operator times the focusing function in a background medium, which is this one here. Yeah. Okay, now that we have perturbations in the pressure fields, you can add these together with the pressure fields in the background medium that I was referring to, and then you will have a total pressure field that we are looking for. And the next slide was showing you, if we apply this scheme to the very same problem, we now get a much better estimation of our reflection of our seismic responses coming from this point. Now you can imagine that, of course, this example is for an individual source position at depth X, but we can do this for multiple positions, and in this context they are called focusing points. Yeah, and this is something that we typically do here at this in this kind of research. And with that, I would like just with some of some of the personal ideas as to why, as a user, I think PyLops is very useful for us. So first of all, is its versatility. So PyLops provides us a very friendly user application interface, and is also very flexible in the sense that it can integrate some other available libraries like NumPy or SciPy and so on. Yeah. Also, that the code syntax it really resembles the actual linear algebra formalism. And what is more important is that we are not required to basically define an explicit, very large matrix to solve an inverse problems, but rather we just use the concept of linear operators. That, I guess, in essence, is a huge advantage for us. Next, of course, it's scalability. So as you hear from Matteo, there is already a support for GPUs using CupY, and there is also PyLops distributed, which uses Dask mainly. And last but not least, I would like to just highlight the great support that is there with PyLops. So it's very comprehensive and large documentation. And also the tutorials is, like these tutorials get you started in a very quickly way with this PyLops library. And I will just finish to say that, saying that there is also a very active and large community ready to help you get started with these operators. And with that, I guess I'm ready to take some of your questions that you might have. Thank you.
Well, thank you, David.
Thanks, David.
Does anyone have any questions here? Sorry, go ahead.
Oh, I was just saying thank you as well.
If there's any questions, feel free to unmute. And okay, if not, I don't know, Matteo, did you have some points that you wanted to bring up for discussion or?
No, I think I just like to say thanks to everyone who joined. And the main point is, if anyone is interested to contribute, or anyone sees something that is missing, but they will really like to have it for their research and they don't know how to make it, just feel free to reach out. We are not a commercial body, so we can't promise in 3 days it's ready, but we can discuss and try to find time to work together on it. And there are quite a few people now that are good, not just in terms of user, but also in terms of knowing what happens under the hood. One of them is Carlos, which is here. I'm sure David is one of them, even if he plays down. So more people can help. Just feel free to reach out.
Cool. Do you have a support channel anywhere, Matteo? Or do you have a support channel or community sort of?
Yeah, so we had maybe I think from now on we're gonna change. I'm probably gonna ask to make a channel on Zwang, because we had our own Slack, but it didn't really fly, and most people reach out to through GitHub, which I think is very good. Just to make an issue is very good. It also keeps track, but maybe we can also make a channel on Slack, Zwang, so people can also reach out there.
I could rename the current one from today, just to PyLops.
Yes.
Cool, I will do that later.
Let's do that. Some people may be leaving, I guess, some places.
Yeah, I think if there's no more questions, if there's no more questions, thanks everyone. Thanks to David, Lukas, and Matteo. That was a great set of presentations.
And
thanks to the coordinators. Yeah, thank you for putting this together. Yeah.
Cool, no worries.
Yeah, thanks very much, guys. Bye.
Bye-bye.
Bye, everyone.
Thank you, everyone.
Bye. Bye.
Okay, bye.
Thanks, everyone.
Thank you.